All right, so we just learned that virtual memory sort of makes things even worse because the operating system and the CPU have to keep track of this virtual memory page table, even if you're not actually using virtual memory. And that page table is big enough on modern systems that it would consume everything in the cache, right? Or take up all that memory. So that's not acceptable. So, to speed up memory accesses, CPUs today have a special cache just for page table entries, known for some reason, and I don't know why, as the translation look-aside buffer, or TLB. So TLBs vary in size from 64 entries to 1024 entries, depending on the chip families. And so your if you're having 4 kilobyte pages, that means that the size of cache covered by a TLB ranges from 256K to 4 megabytes of memory, which still isn't a lot, but at least we have a special spot dedicated to page table entries. Some TLBs on more modern processors do allow really large pages, like 1 megabytes to a few gigabytes, but the operating systems sometimes don't provide super good support for that yet. So anyway, we have these TLBs. We have this issue now. There's sort of several different things that we're fighting against. We're fighting against RAM bandwidth. We're fighting against network bandwidth. We're also fighting against contention for RAM and the network. And we have to fight against this virtual memory paging problem. So what can we do? What are some things we could do to try to avoid all those problems? Well, basically, you would have to design your algorithm really carefully and do a cycle where you design and then try it out on the actual software and hardware that you're going to be using. And software meaning the operating system and the network interconnect stuff, the MPI software. But we would put that in a circle of development, trying to design so that every core's subproblem fits entirely in the core's level 3 cache, the one that's closest to the core. Okay? So we're going to try to design everything so that whatever we're working on fits in that amount of memory, while simultaneously designing so that its subproblem page table will fit entirely in the TLB. So its total memory that it's going to use is in that TLB range, so we don't have to go out into memory to look at the TLB and then look in memory, right? So we don't have two RAM accesses. Okay, so as a rule of thumb, those previous two items mean that we want the core to be working on subproblems that are no bigger than a few megabytes apiece. Then we would also want, if we can, design so that our program makes infrequent but large communications. So when it's going to start sending data, it doesn't do it very often, but when it does, it's going to send a lot, because the latency for starting up the communication is very expensive. And then after that, the subsequent byte by byte communication costs are very, very low. We might also then think about using in MPI programs a non-blocking send. So the MPI send function that we used in our previous module, when I invoke MPI send, my program halts at that point and nothing happens underneath it until that send is complete. Well, an iSend is a non-blocking send, which means that once I execute the send, I let the network and the MPI infrastructure handle the sending, and I just keep going. So we would try to, while the send is happening, do some more computing. And if I can do that, if that's possible, then I can sort of decrease the cost of the communication to zero, because I'm actually doing useful computing while the communication is happening. That makes our programs a lot harder to design, though, because now the programmer is more responsible for the synchronization than with just the primitives that we looked at in the previous module. Maybe in the long term, what we do is we buy chips with bigger caches and TLBs. So as computing moves forward, we could start to see those areas be increased as a way to further increase the performance of CPUs, particularly in a parallel environment. All right, that about sums up this module. Just to circle back and talk about the storage hierarchy in light of what we've learned through OpenMP and OpenMPI. Our next module, we'll talk about high throughput computing, which is a slightly different way to do parallelism.